So today we're going to be learning about how is it that we write down our recipes for chemistry. Oftentimes you will be given a description of a reaction, and then we need to translate that into a way that we can work with it. Let's start today with an example. So here I have a lighter. Anybody know what they put in these lighters? Yeah, excellent, butane. Now, for those of you that did your homework, butane is actually tetracarbon decahydride. But we're going to say here butane reacts with what? When I light this on fire, what is butane reacting with?
Oxygen.
Yeah, excellent. It's reacting with oxygen. So it's reacting with oxygen gas. And what is produced as a result of this reaction? Whenever we burn hydrocarbons or fossil fuels, what is one of the things we're producing? It's heating up our planet. It's going to heat up our planet. What is one of those greenhouse gases we're concerned about?
CO2.
CO2, carbon dioxide. So that's one of the products. So butane reacts with oxygen gas to produce carbon dioxide. And the other one you probably don't know, but whenever you combust something, you're going to produce also water. You are going to produce water. So oftentimes when I give you a problem in chemistry, it's going to look like this. I'm going to say, iron metal reacts with oxygen to form iron 3 oxide. Maybe I switch up the wording. Maybe I say one way to produce carbon dioxide in water is to react butane and oxygen. So the wording can change, but very often you're going to see some key terms here. What are some of the key terms you see here? If you had to pick out some key terms. Yeah, excellent. Reacts with is one of those very key terms, right? You may see combined, you may see reacts with. What else? What's another key term? Yeah?
To produce carbon dioxide.
Yes, to produce. Those are some very key terms you need to watch out for, because that's going to tell you what's reacting and what is being produced, what your reactants are and what your products are. And actually, before we do anything else, let's start with that. So what are reactants in a reaction? What are reactants? Well, these are going to be the elements or compounds that you start with. It's going to be the elements or compounds that you start with. So in this case, we started with butane and oxygen. And then we produced what? What were our products here? Yep.
CO2 and H2O.
CO2 and H2O. So here in our example, our reactants were butane and oxygen. And for our products, it was CO2 and H2O. So this is going to be the elements or compounds that you end with. And in the case of our example here, that was going to be, I'm not put this yet. That is going to be carbon dioxide and water. So it's really important you can tell what the reactants are and what the products are. What are we starting with? What are we ending with? So this is how you're going to be presented with information, but we need to turn that into something useful, our recipe of chemistry. And there's one of two ways you can do that. You can either use a word equation, and by the way, this is my shorthand for equation. A word equation is going to utilize the chemical names of everything in order to come up with an equation. So I'm going to keep it very simple here. I'm just going to say it uses the chemical names. And what do you think a chemical equation does? What are we going to use in the chemical equation? We're not going to use the names. What are we going to use? The formula is excellent, right? We're going to be using the chemical formulas. So when we have a description of a reaction, we can parse it into two ways. More often than not, we are going to be using chemical equations, but word equations are a great way to practice going from word to chemical formula, which is probably the most commonly used skill in all of chemistry. And today, most students are confused. Sorry, Sabir, are you okay?
Yeah.
Is your friend outside the window there? Or? No? All right. So word equations, chemical equations, are the way we parse that information. And more often than not, we're going to be using chemical equations here. But going from word to chemical is a very valuable skill. So let's do that. Let's write down our word equation. Let's write down our chemical equation. Now there are a couple rules that apply to both word and chemical equations. So you are going to separate the reactants and separate the products with a plus. Okay, so your reactants, if you have multiple reactants, you will separate them with a plus. And if you have multiple products, you will also separate them with a plus. Anybody know, how do we separate our reactants from our products? You've seen it before, trust me. But how do you separate them? You separate them with an arrow. So we separate the reactants from the products with an arrow. Now, with your arrow, the tip of the arrow is going to point to what? The tip here, is it going to point to the reactants or the products?
I think the product.
The products, right? And your tail is going to point to the reactants. So you're going to have your tail pointed to reactants, tip to products. So we'll say here the tip to the products and the tail to the reactants. So now let's go back to our example and let's write down the word equation and the chemical equation. Let's write down both. So with our word equation, what are our reactants? We already talked about this. What are the reactants for this example? You guys literally wrote it down. What is it? AP, what is it?
Butane and oxygen.
Thank you. Butane and oxygen gas. Now, butane technically is tetracarbon decahydride, technically. And then we're going to separate these compounds with a plus. So whenever you have multiple reactants or products, you must separate them with a plus. So tetracarbon decahydride reacts with oxygen gas to produce, right? To produce, that's really what that arrow means, to produce carbon dioxide and water. So tetracarbon decahydride reacts with oxygen gas to produce carbon dioxide and water. Now, most students can do this just fine, no issues. Where they struggle is going from word equation to chemical equation. And the reason they struggle is not because this new skill is challenging. They struggle because they still haven't fully learned bonding, how to go from name to chemical formula. So let's test your knowledge a little bit. What is this one here? Tetracarbon decahydride. What were the Greek prefixes tetra and deca? Yeah?
Tetra is 4 and deca is 10.
Excellent. So we have 4 carbons and we have 10 hydrogens. What's oxygen gas? What's oxygen gas?
O2.
Ah, excellent. Why'd you say O2 and not just O? Why is that wrong?
It's because you don't find those in nature, I think. What was it?
Yes. So what? You're right. What was the name we gave to these elements that in nature don't exist really by themselves? They pair up. These are your diatomic molecules. Right? Remember Hofbrinkel, the creepy chemistry clown? So very important, whenever you have one of those Hofbrinkel elements by itself, you need to make sure you pair that element up. Lots of students forget about that, they lose a ton of marks, and also your recipe won't be correct, right? Instead of using a whole egg, you're only using half an egg and things get all weird, right? So very important that you have the correct ingredients. So if you ever see oxygen gas, hydrogen gas, chlorine gas, any of those Hofbrinkel elements, they must pair up. What is CO2?
CO2.
What is carbon dioxide? CO2! And what is water?
H2O.
H2O. So that one's pretty simple, because honestly, covalent compounds, in my mind, are much easier to go name, formula, name, if you remember your Greek prefixes. Right? You have to have those memorized, by the way, for your unit test. But let's look at a tougher example. Let's look at a harder example now. Let's say you had say, I don't know why I've been on a vanadium kick recently, but let's say vanadium 5 sulfate reacts with, actually, no, we'll keep it like that. Vanadium 5 sulfate reacts with magnesium phosphate to produce vanadium 5 phosphate and magnesium sulfate. Okay, so there's another example for you. Keep in mind, your reactants might not always come first when I write these down. That's why I kind of hesitated there. I was going to think about switching it around. I could also word this: one way to produce vanadium phosphate and magnesium sulfate is to react vanadium sulfate with magnesium phosphate. Right? So be very careful of those key terms, right? Wherever you see reacts with and to produce, right? Be aware of those key terms. Okay, so I'm going to let you try this one on your own right now. Then we'll come back in a second and do it as a class. Okay, so the word equation. Someone want to share what they put down? Who has the word equation? Where's the mono coming from? Is vanadium sulfate a covalent or ionic compound? Is it covalent or ionic? It's ionic, right? We have the names already, right? We don't need to add anything to them. It's literally just putting them in the right order, right? Because we were given our reactants, right? Vanadium 5 sulfate reacts with magnesium phosphate. Vanadium 5 sulfate reacts with, I'm going to run out of room here, magnesium phosphate to produce vanadium phosphate. As I walked around, pretty much everyone had this correct. Vanadium 5 phosphate and magnesium sulfate. Where many people were struggling was going from word equation to chemical equation. Question? No. Now, when you go from word equation to chemical equation, people are often overwhelmed at all of the work they have to do. Just tackle it one at a time, right? Treat each of these as a separate individual problem. So we know vanadium 5 sulfate's an ionic compound. So what were the steps you had to do to determine the formula for an ionic compound? Yeah.
I have to figure out the charge.
The charges. And what does this 5 represent? It's the charge on vanadium. So we know the charge on vanadium is 5 plus. What is the charge on sulfate? 2 minus. SO4 2 minus. Right? Don't forget to check the table of ions to find that charge. Now, what were the 2 questions you have to ask? We need to know the total charge, which is the, your lowest common multiple, right, which is your total charge. That'll be 10 electrons donated, 10 electrons received. And then you have to ask yourself, how many of each ion I need as a result. So how many vanadiums do I need? 2. Excellent. And how many sulfates? We need 5. So that means our chemical formula is V2SO4 5. And be careful here, I still saw a couple people making the mistake of doing this, no brackets. What does that become if I don't put brackets? Yeah?
SO45.
Yeah, it's saying I have 45 oxygens. That's crazy town, right? So we don't have 45 oxygens, we have 5 sulfates. Now, I want you to get to the point where you're able to do this pretty instinctually, right? That'll come with practice. But for now, it's important you treat each of these as a separate problem while you're doing it. So I'm going to quickly just rush through the other two here. I'm not going to go through the steps. Who here thinks they had the right formula for this one? Vanadium 5-phosphates. Yeah.
I wrote V3.
Yeah.
In brackets PO4, followed by another bracket 5,
Excellent.
plus MgSO4.
Excellent. Well done. So, again, if you were one of those people that struggled with coming up with these chemical formulas, this was a tough question to be honest, you need to tackle it individually and go through the steps, show your work, right? Students often freeze up, they don't know what to do because they're trying to do it all in their head, right? Show your work, go through the steps, practice it the right way, and eventually you'll get to the point where you're comfortable and you can pretty much just do it in your head. Any questions at all?